Hey guys, this is section 5.3, polynomials and their graphs. So what is a polynomial? Well, a general polynomial is written below. It's written as an xn plus an minus 1 times x to the n minus 1 plus dot 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 plus a2 x squared plus a1x plus a0, where n, all the n's are positive integers, and an is an integer. So what does that really mean? Well, basically, it's just a bunch of pluses and minuses of numbers in front of x to some power. The only restriction is that the power of x has to be basically a whole number, a positive whole number. So we have a few examples here. We have x squared plus 10x plus 25, which you guys know is a parabola. But because this also fits into our definition of a general polynomial, a parabola is also a polynomial. And we have a couple other examples here. Something like h of x equal to x to the 7th plus 20x to the 5th plus 10x squared plus 11. And so really all it is x to a positive power plus a number in front of another x to some power and a whole bunch of addition and subtraction. So I could change that to subtraction. It's still a polynomial. And so every polynomial, as you can see how I've written it so far, is that we have a sort of like descending way of writing the powers. We typically write the largest powers first in descending order. So this has 7x's multiplied, 5x's multiplied, 2x's multiplied, and the 11 has no x's multiplied. And g of x may not look exactly the same, but what you'll find is if you expand this, and what I mean by that is if you FOIL it, you can see what the expanded form looks like, and it'll look somewhat similar to f of x and h of x. So we have a definition here, the leading term. And the leading term of a polynomial is just the term with the highest power of x. So for f of x, the leading term would be x squared. For g of x, if you expanded this, you would see that the leading term would be x cubed. Okay, and I'm just going to change this one for instance. And so the leading term of g of x would be x cubed. But for h of x, we have a 2x to the 7th. And so the leading term incorporates the coefficient in front of the x to the 7th. So not only is the x part of the leading term, but the number in front of it too. So the leading term here would be 2x to the 7th. Okay, so hopefully that's pretty straightforward. So one of the nice things about polynomials is they are smooth, continuous curves. And basically what that means is that when you draw a polynomial or you graph a polynomial, it's always going to be a smooth curve with no jagged edges, and you can draw a polynomial without having to pick up your pen. So you can put your pen down and draw smooth curves without lifting, then you have a polynomial. So we have a couple pictures down here to show what some functions that may be polynomials and some that may not be. So here we have essentially the picture of a line. Is this a smooth continuous curve? Can I draw this function without lifting my pen? Yes, I can. And is it smooth? Does it have any like sharp corners? No, it doesn't. So this is a polynomial. And in fact, functions lines y equals mx plus b are in fact polynomials because they satisfy the general polynomial form as well. For instance, y equals 2x plus 3, right? This is a line, and it satisfies the fact that integers, positive and negative whole numbers, are essentially the coefficients, and x has powers that are positive, right? This one has 1 and none, right? And so that fits our definition of a polynomial. So is this graph here a smooth continuous curve? And so it is continuous, right? I could draw this picture without picking up my pen. However, it has a jagged edge, like a corner. And so this is not a polynomial. And in fact, the image I was trying to draw is the absolute value function, which we know isn't a power of x to a positive power, right? It's this absolute value function is essentially looks like a v, which has a jagged edge, so the absolute value would not be considered a polynomial. And also, it doesn't satisfy our definition of what polynomials look like: sums and differences of positive, non-negative x powers with whole number coefficients. And so hopefully it's seeming pretty obvious that this is a continuous curve, right? There's no jagged edges, so this is a polynomial. Likewise, this is a smooth continuous curve. I can draw it without picking up my pen, and there's no jagged edges, so this is also a polynomial. And so is our final picture. I can draw this U shape without picking up my pen, and it's also a polynomial. But this one you also should recognize, this is a graph of a quadratic, right? So something x squared, and because it's an upward facing parabola, we know that the x squared, the coefficient of x squared is positive. Okay, so here's another definition and something that we need to characterize, and it's called end behavior. And essentially, end behavior is just the behavior of the function towards the end of the number lines. So we want to know, what is the function doing as x gets really big positive? So as x, I'm just going to draw a little number line, a little Cartesian plane. What is the graph doing as x is way, right? We have positive x's here, we have negative x's here. What is the picture doing as x is way over here? Is it going up? Is it going down? Is it remaining flat? That's the type of stuff that we want to know. Likewise, we want to know what the graph is doing on the negative side, right? Towards like negative infinity. So we have positive infinity somewhere over here, negative infinity somewhere over here. We want to know, what is the graph doing as x is getting really big negative? Is it going up? Is it going down? Is it remaining constant? Is it doing some weird stuff where we can never tell? We're really interested in what is the function doing as x approaches both positive and negative infinity. And so to kind of guide our intuition, we can think about some of the functions that we already know. So think of the even function x squared, a function that we've been working with basically the entire semester so far. It's a quadratic, so the picture is a parabola. And so what does the function positive x squared do as x approaches positive infinity? So what's happening as we're going towards this side of the number line of x? Well, you can see as x is getting really big, since this arrow is kind of slanted, y is also getting really big. So in this case, as x approaches positive infinity, y is approaching positive infinity as well, right? And likewise, as x approaches negative infinity, as we tend towards this side of the axis, x-axis, what is the y value doing? Well, this is also going to positive infinity. So for the end behavior of an even function, or a parabola in this case, as x goes towards negative infinity, it also goes towards positive infinity. And we know that because both of the arrows point up. So this is how we would describe the end behavior of an upward-facing parabola. But what about a downward-facing parabola? Well, as x goes towards positive infinity, right, as we move more and more to the right, you'll notice that here y is going down, right? It's getting big negative. So as x approaches positive infinity, y is becoming negative. It's getting larger and larger negative. And also, as x approaches negative infinity, y is approaching negative infinity. So anytime you have an even function, you know that as x approaches positive infinity, it's going to be up. As it approaches negative infinity, it's also going to be up. And if you have a downward facing even function, then the opposite will be true. So essentially, if you have you have an even function, your arrows, essentially your end behavior, for both the positive and negative side of the x-axis will be the same. They'll either both be facing up or both be facing down. And so not only is this true for parabolas, but it is dependent on the leading term. So the end behavior of a polynomial will always be determined by the leading term. So what do I mean by that? Well, if I have a function or a polynomial, and I'm just going to come up with it on the fly. If this is my polynomial, 2 times x to the 8th power plus 3, because 8 is an even number, the end behavior of this polynomial is going to match the end behavior of x squared. Okay? And if I come over here and I say, well, what if I have g of x, but this one instead is equal to negative 3 x to the 6th power plus 5x squared plus x plus 2. Well, because the leading term here is even, just like 2 is, but the coefficient is negative, just like the downward facing parabola, the end behavior of this function is going to match the downward facing parabola. And so if we think about odd functions, and we can think of x cubed, as x goes towards positive infinity, what is y doing? Well, y is also going towards positive infinity, right? It's getting bigger and bigger positive. As x approaches negative infinity, so as we go this way on the x-axis, what is y doing? Well, as we go towards negative infinity, y is also going towards negative infinity, right? It's going down. If we have a negative x cubed, the picture flips, and so we have, as x approaches positive infinity, what is y doing? Well, this time y is going towards negative infinity, right? Our y's are becoming negative. And as x approaches negative infinity, so now as we move towards this side, what is y doing? Well, y is going towards positive infinity, right? It's getting larger and larger. And so, kind of in the same manner, if we have a polynomial that has an odd term as the leading, an odd power as the leading power for the leading term, the end behavior of this function is going to match the end behavior of x cubed. Likewise, if we had a function negative 3 of x to the 9th plus 7x squared plus 2, because this is the leading term, the end behavior of this polynomial is going to match the end behavior of the negative x cubed. And so you may be asking, well, why is this? Is this just a coincidence? Well, no. What's happening is, as x gets really, really big positive, right? So you can think of a number like 10,000, for instance. Okay, so let's say x is equal to 10,000. When we plug 10,000 into this function, into g of x, what's happening? Well, 10,000 is going to be raised to the 9th power, right, which is going to make the number huge. And then we're going to multiply it by 3. So it's going to be a really huge negative number. And then we're going to plug it in here, but this time we're only going to square 10,000. And so the fact that as the x's get larger and larger, these terms right here, the non-leading terms, have less and less of an effect on what the y value is when we plug in these large x's. And so hopefully you can see that when we plug in x equals 10,000 into here, this number is going to be so big negative that essentially adding 2 to it, if you can think of it as adding 2 to negative 10,000, it's really not going to affect the value of y all that much. And so the idea though isn't that we're just adding 2 to 10,000, but 10,000 to the ninth power, which is going to be astronomically large. And it's not even that we're stopping at 10,000, but we're approaching infinity, right? So these numbers are even larger. They're unfathomably large. So when they're unfathomably large, adding 1 or 2 or even 1,000 or 10,000 isn't going to make a difference in terms of what the graph is doing at the end of the number line, right? And so that's why these functions, regardless that they have all these extra terms, they're still going to behave like the biggest term in the leading term of the function. Is just going to be driving the function more than all of the other pieces combined. Okay, so this is kind of what we're saying here. The end behavior of a polynomial will always be determined by the leading term. So basically, what you have to do is just make sure that when you have a polynomial, that it's written in descending order of power, right? So you have the largest power of x at the front, so you can accurately determine what the end behavior will be. Sometimes that will require some rewriting of the problem. Okay, and so here's another definition. We have multiplicity. And so multiplicity basically talks about how many times the same x-intercept appears. And so this will be important because it'll help us sketch our polynomials. So as an example, assume we have f of x, right? And it's x plus 5 squared times x plus 3. And so luckily, this function is already given to us in factored form, which makes our lives a lot easier. So why is that? Well, because we're able to find the x-intercepts a lot easier. But first, let's try to figure out what the end behavior is. And to do that, all we really need to do is determine what is the leading term and whether that leading term is positive or negative. Because we really only have 4 options here. If the leading term is an even power and it has a positive number in front of it, the end behavior is going to match the upward facing parabola. If the leading term is even, but it has a negative coefficient, it's going to have the same end behavior as the downward facing parabola. If the leading term of our polynomial has an odd power, but a positive coefficient, it's going to have the end behavior of x cubed. So as x approaches positive infinity, it'll go to positive infinity, and as x goes to negative infinity, it will come down to negative infinity. And likewise, if the leading term of our polynomial is an odd power but has a negative coefficient, then our end behavior will match that of negative x cubed. Okay, and so these, for polynomials, these are the only 4 options you have. No matter how large the polynomial gets, it's going to, the end behavior at least, will be one of these 4. Okay, so to figure out what our leading term looks like, we need to expand this polynomial. And so some of you may be able to see that you can already see what the leading term is without having to expand it, but let's go ahead and do it anyway. And so x plus 5 squared, that's x plus 5 times x plus 5. And so if I expand this, we're going to FOIL, right, this way and that way. And what I'm going to get is x squared plus 10x plus 25. And then not only do I have those 2x plus 5 squares, but I also have to multiply that times x plus 3. And so now I need to FOIL this way, and when I do that, what I'll get is x cubed, x times x times 10x plus 10x squared, x times 25, 25x, and now the 3 multiplied times anything, plus 3x squared plus 30x plus 75. And now I can count my like terms and add them together. And so my function in expanded form will be x cubed plus 13 x squared plus 55x plus 75. And hopefully you can see that even though I've expanded this, if we have an x squared, we know we're going to have these 2 x's eventually being multiplied, right, to get that x squared, and then these 2 x's will eventually FOIL and multiply times this x. So you don't necessarily need to expand it if you can see that this 2 tells me there's 2 x's here and there's no coefficient here, so it's just my ending coefficient is going to be a 1. And then we're going to multiply times this x, which has a coefficient of 1 as well, so it's not going to change. So essentially, just by looking at this, you can see that my ending coefficient is just going to be 1x cubed. But if you can't see that, go ahead and expand. And so now we know what our leading term is. It's an x cubed, and so we know our end behavior now. So what does that mean? It just means that as x approaches positive infinity, what is y going to do? Well, y is going to do the same thing it does for the regular x cubed function. It's going to go to positive infinity. So, and what is x going to do as it goes to negative infinity? Well, as x cubed goes to negative infinity, we know that y will go to negative infinity. So this function has the same behavior as the general cubic function. So it's going to match this green one right here. Now, in this example, it just so happens that our leading term is x cubed, but it doesn't matter whether it was x cubed or x to the 7th or x to the 9th or x to the 11th. As long as it's odd, it's going to have the same end behavior. Okay, so the fact that it was 3 is just a coincidence. So we know, so what does this tell us? That means we know when we draw our graph, as x approaches positive infinity, we know y approaches negative infinity. So our arrow is going to be somewhere here. Likewise, we know as x approaches negative infinity, as we go this way towards the graph, y is going to approach negative infinity. So we're going to have an arrow down here doing that. Okay, so we're already starting to sketch a little bit about what our function looks like. Okay, so now let's get our x-intercepts sorted out. If we want to find our x-intercepts, what do? Well, we do the same thing we always did to find our x-intercepts. We set y equal to 0, right? And in this case, y is f of x. So if we set f of x equal to 0, so we can do that over here. If we set f of x equal to 0, that tells us that 0 is equal to x plus 5 squared times x plus 3. And hopefully by now you can see that we're using the zero product property. So 0 is equal to x plus 5 times x plus 5 times x plus 3. And so when are these three things going to multiply to 0? Only when the inside of the parentheses is equal to 0. So all we need to do is take the inside of these parentheses and set them equal to 0 and solve. And if we do that, we should get x equals negative 5, x equals negative 5, and x equals negative 3. Okay, so our x-intercepts are negative 5, comma 0, negative 5, comma 0, and negative 3, comma 0. And so this multiplicity definition that we had here, you'll notice that we have the same x-intercept twice. So if you have the same x-intercept an even number of times, that means when we plot our point, our picture is not going to cut through the x-axis. So if your multiplicity is even, if you have even multiplicity, so even multiplicity, you're going to touch the graph but not cross it. And so this is kind of similar to what x squared does, right? Sometimes it can touch the graph and come back. And if you have an odd multiplicity, that means you're going to cross the x-axis. So I shouldn't say touch the graph, I should have said touch the x-axis, excuse me. And so all that means is that when we get to draw this point, instead of crossing it like this, because negative 5 has an even multiplicity, if we're starting from below, we're going to touch it and then come back down. Okay, we're not going to go through the point. But let's go ahead and plot our second x-intercept, negative 3. So that's negative 1, 2, 3. So there's our other point. And you know what? Let me do this in a separate color. So red will work better. So here's my end behaviors, where my arrows are going to end up. I have my x-intercept with multiplicity 2 there, and my x-intercept of -3 there. And so the only thing left to find now is our y-intercept. And how do we find our y-intercept? Well, the same way we always do. We set x equal to 0. And so because this function, we did the work of actually expanding it, we know that f of x is actually equal to this too, right? This was our expanded form. But what happens when you plug in x equals 0 into this function? What is f of 0 going to be? Well, that means just plug in 0 for all of our x's, and 0 to any power is always going to be 0. So this becomes 0, that becomes 0, 0 times 13 is 0, 0 times 55 is 0, and so the only number we have left is 75, right? So f of 0 is actually going to be equal to just 75. So that's a very large number. So what I'm going to do is just call this 75. I'm just going to kind of cheat a little bit just for the sake of having an easier graph to draw. And so I know I'm eventually going to cross here, right? I'm going to cross the y-axis here. And so now all that's left to do is essentially connect the dots. Let me draw that arrow a little nicer. So we know we're starting in the left corner of our graph, and we have to come up and touch this point, right? But we know because it has multiplicity 2, which is an even number, we're not going to cross it. We're just going to touch it and come back. And then we have to cross our x-axis at -3 because we have an x-intercept. But because this one has multiplicity 1, we know we need to cross it, right? This one had multiplicity 2, which is even, and so we just touch that point. And so when we come back up, try to draw that a little nicer, we're going to cross this time, and we have to run through the point 75, and our end behavior is going to finish here, so we could do something like that. And so remember that these are just sketches, and obviously mine is a terrible sketch because I didn't allocate enough room to draw graph 75, but I'm going to try to do this one more time and make it a little nicer. So instead of drawing my arrow here, I'm going to erase a little bit of this and draw my arrow up here, still in the upper right hand corner. And so here I'm going to touch and come back, but this time cross, go through 75 and continue on to infinity. Okay, so we know our y-intercept here was 0, 75. And so these are essentially the 3 things that you need to look out for to figure out how to graph a polynomial. So let's go ahead and do one more example, and then we'll call the end of the video there. Okay. So let's say our function f of x is equal to x squared plus 12x let's see, plus 20 times x plus 7 times x plus 5 squared. And actually, let's change some of these to negative, just to have a little bit of different stuff going on. Okay, so what do we need to do? Well, we need to find the end behavior. We need to find the x-intercepts, just like we did before, and we need to find the y-intercepts. Remember that when we find the x-intercepts, we need to worry about their multiplicity because that tells us whether the function crosses or just touches and comes back. So what is our end behavior? Well, if I look at this part of the polynomial, if I square this, what am I going to end up with here? What's the biggest power of x I'm going to get? from just this part? Well, that's going to give me an x squared. This part of the polynomial is just going to give me an x, right? And then I'm going to change this at the last second. Let's make this negative and make this positive. So this one's going to give me a negative x. And the biggest x in this part of the polynomial is x squared. So if I multiply all these together, this is going to give me my leading term. So x squared, negative x, and x squared. So that's x to the fourth, x to the fifth, but negative x to the fifth. Okay? So what I can do here is I can also just write my leading term if that's going to help me figure out my end behavior. And so my leading term is going to be negative x to the fifth. And if it's negative x to the fifth, then I already know what my end behavior should be. It's the same as the end behavior for negative x cubed, because it's odd, so it's going to follow the same end behavior. And because the coefficient is negative, rather than following the behavior of x cubed, it's going to follow the end behavior of negative x cubed. So as x approaches negative infinity, x is going to approach, y is going to approach positive infinity. And as x approaches positive infinity, y is going to approach negative infinity. And so I can already start sketching out my graph here. Try drawing the straight line one more time. So that means as x is going towards negative infinity to the left, y is going to positive, so now my arrow ends up here somewhere. And as x goes to positive infinity, I know my y is becoming negative, so I know my arrow ends up here somewhere. Okay? Cool. So now I need to find my x-intercepts. Well, recall that when we're looking for x-intercepts, we do the same thing we always do. We set y equal to 0, and so I have 0 is equal to x squared plus 12x plus 20 times negative x plus 7 times x minus 5 squared. And so we're going to use the zero product property, but you'll notice that this is a trinomial. So you may have to factor something to be able to find all your x-intercepts. And so since this one is a pretty simple one, we're looking for two numbers that multiply to 20 but add to 12. And so I'll give you a second to try to figure that out. And hopefully you figured it out by now, but the numbers that multiply to 20 and add to 12 are 10 and 2. And so because the coefficient of this quadratic is 1, it's just going to factor into those two numbers, x plus 10 and x plus 2. So using the zero product property, I have all of these things being multiplied, right? And equaling 0. That just means any of these has to be 0. So I can take the inside of the parentheses, set it equal to 0 and solve, and that gives me x equals negative 10, x equals negative 2, x equals positive 7, x equals 5, and x equals 5. So my x-intercepts are going to be negative 10, 0, negative 2, 0, 7, let's write it in ascending order, 5, 0, 5, 0, and 7, 0. And recall that 5 is the only one with multiplicity even, right? Because it has multiplicity 2. And so that means when I draw my x-intercept here, I have to remember to not cross the x-axis, but to touch it and come back down or go back up. And so say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3, 4, 5, 6, 7. Okay, so this is one of my x-intercepts. Negative 2 is another x-intercept. Positive 5 is another x-intercept. And positive 7. And so let me do that with a different color again so it's more visible. So negative 10, 0, negative 2, 0, plus 5, 0, and plus 7, 0. Okay, And so now let's find our y-intercept. And how do we do that? Well, we just we set x equal to 0, right? So we know for our y-intercept, x is going to be 0. And what happens when we plug x equal to 0 in here? Well, 0, if we plug f of 0, we get 0 squared plus 12 times 0 plus 20 times 0 plus 7 times 0 minus 5 squared. And so this portion here is going to give me 0 squared plus 12 times 0 plus 20 is just going to give me the 20. 0 plus 7 is just 7. And 0 minus 5 is negative 5. But negative 5 squared is going to give me positive 25. And so my y-intercept is massive this time. Once again, it's going to be 20 times 25, which is 500, and then times 70, so it's going to be 3,500. Okay, that's a very large y-intercept. So this is just because I'm making stuff up on the spot, but the books and the problem won't have numbers this insane. I can guarantee you that. So I'm just going to put a little dash here and put that this is 3,500 and make a little dot there. We know it's positive. That's really the main part of sketching the graph. And so all I have to do now is kind of follow my intuition about where the arrows are. And remember that if I have even multiplicity, if I have even multiplicity, I touch and go back, I don't cross. But if I have odd multiplicity for my intercepts, I cross. So we start with our arrow somewhere over here. And because negative 10 has we only have one of those intercepts, it has odd multiplicity. So I'm going to go through the x-axis. And then negative 2, right, this intercept right here also only has 1. So I know I have to go through that one. Okay, but now I have my y-intercept to get through. And I don't have any x-intercepts between it. So I know I have to get all the way up there. I'm going to have to touch this. Then I need to get to 5. And because I'm coming down to 5, because it has even multiplicity, I know not to cross. I need to touch and come back. But at 7, because it has multiplicity 1, I need to cross. And since I know my end behavior ends down there, I can tell that I've done basically everything correctly. And I just need to connect to my arrow. And what I'm going to do, because I can't draw, is to just draw a new arrow. And so this is a sketch of the polynomial x squared plus 12x plus 20 times negative x plus 7 times x minus 5 squared. So hopefully this seems pretty simple. If you guys have any questions, feel free to reach out during office hours or through Discord. And I'll see you guys in the next video.